We're continuing our look at aliasing. If you look at the book, you should read this section 7.4.2, that whole section on aliasing. We've seen that it's a process that results in false low frequency signals if the sampling frequency is not high enough. If we have a real image made up of a whole lot of frequencies where the highest frequency is F max, then we know we should sample that at a frequency, this is frequency here, greater than twice F max. So it would be a way out here. It has to be more than double that F max. If we don't, if we have a sampling frequency that's not more than double F max, say it's out here, and half of that sampling frequency is here, the Nyquist frequency, we cannot capture any frequencies higher than the Nyquist frequency. And any frequencies in the real signal above the Nyquist frequency, such as these ones here, would get mirrored down and reappear as lower frequencies below the Nyquist. And then that would add on to this part of the spectrum. This here would appear up here, and we would get a signal which has a frequency spectrum like that. So it's a double whammy, really. We get nothing above Fn, and the frequencies above that get mirrored below and add on to the frequency, and we get a really corrupted shape to our observed spectrum. In order to avoid aliasing, we have to ensure that the sampling frequency is way bigger than the largest frequency we're trying to capture. At least twice, but better 3 or 4 times that. If not, we get aliasing. And if you can't sample at a high enough frequency, then you need to pre-filter the analog image so that it has no frequencies above Fn if your Fs is fixed. I want to look at Module 4 again on sampling theorem and aliasing. If you open that up, there are 2 documents. I want you to read this document here, and I want you to download this exe file, which is a little program. If you start up that program, this will appear. We're starting off with a sine wave here, and sampling it. This is the time. We're sampling it every 10 nanoseconds. This is 200. We're sampling it every 10. That is, the sampling frequency is the inverse of that, is 100 megahertz. What is the frequency of the sinusoid that we're trying to sample? Its frequency is given by the inverse of its period. Its period is the time up to here is 250 nanoseconds, and if we invert that 1/250 times 10 to the minus 9, we get 4 times 10 to the 6, 4 megahertz. You should try that on paper to make sure that you get that. So we've got a 4 megahertz sinusoid and a sampling frequency of 100 megahertz, 25 times more. We don't expect any problem. We're taking a lot of samples during each period. The sampled wave is actually going to look like this here, but when we come to reconstruct it, we'll be able to do sync reconstruction and get the sinusoid out of it. So the frequency spectrum of that sine is that, a single spike at 4 megahertz. Frequency is 4. And this one is 4 megahertz, plus a little bit of high frequency jitter, if you like, but we don't see it here. Now we can change the sampling frequency and keep on reducing it. Time between samples is increasing, the sampling frequency is reducing, and this here will be the sampled sinusoid. and it's still looking not too bad. Remember, it's a 4 megahertz sinusoid initially, but when you start getting down to 4 times that, you're picking up little bits of problems. Those high frequencies are not so much the problem, it's the lower frequency ones that we should worry about. When we get down here, it's 4 is the frequency that we want. When we get down to, we've got a lot of mirrored low frequencies here, which are corrupting the signal. There's our 4 megahertz. We're just about at the Nyquist criterion here. If we go below that, we get a lot of components here at less than 4, and in fact, soon we get more components at less than 4 megahertz than the original 4 megahertz signal. So things get really bad. You can see them bad here. You can see them bad in the frequency domain. We're now getting a signal at 3 megahertz, which is bigger than the 4 megahertz component, and we expected just one component at 4 megahertz. So I want you to play around with that a little bit and use different waves here. This is a 3-term sinusoid. It has frequencies at here, wherever that is on the scale, and here and here. These two have the same amplitude, and this has a smaller amplitude. This is the composite, and we can start off, sampling a lot of times so that we get much the same thing and see what happens. Follow what happens as we go down in sampling frequency and as we take it up. I want you to try that and on the other options here. Now this aliasing we can see in videos or movies. Used to be called the wagon wheel effect in westerns, but now we see it with car wheel effect due to the car wheel covers. When a car accelerates from rest, the wheels appear to move forward to begin with, and then at some speed they appear to move backwards, even though the car is still accelerating forward. And then at a higher speed, they'll move forward again or appear to move forward. And then at a higher speed still, we might see them appear to move backward. So this is all aliasing, and it's due to a limited sampling frequency. Our sampling frequency is 30 frames per second. So I want you to look at module 4 and be sure you've covered everything in there, including these, and look at this and look at the wagon wheel effect. And also if you could do activity 7.5 from the book.